Presentation is about how to extend the longevity of a car and to enhance fuel economy. Well, it can be achieved simply by changing engine oil in a car. And we developed such engine oil that enables to get fuel savings up to 30% and to achieve radical extension longevity of the car engine as wear rate in the engine is reduced into 25 times in comparison with the best synthetic engine oils. The oil is comprised of palm olein as the base fluid and it is enhanced with a special pack of additives. While such formulations of engine oil can be used only for tropical climate, we also work on engine bio-oils for countries with colder climate. If we estimate how much energy is lost to friction, then we may conclude that it is more energy lost than it is delivered to wheels. And indeed, 10% of fuel energy is lost in the engine, 5% is lost to overcome friction in transmission, differential and various bearings, while only 12% of the fuel energy is used to move the car. With proper lubricants, we may considerably enhance fuel economy of modern vehicles. Longevity of modern cars is limited mostly by wear of an engine that is normally lasting of 10 to 12 years. Other parts of the car can be designed to serve longer or be replaced easily, so we can dramatically extend a useful lifespan of vehicles if we reduce wear in the engine. Any engine oil comprises so-called anti-wear additives. Mostly these are zinc dithiophosphate, ZDDP, commonly called as zinc, despite the substance comprises more sulfur and phosphorus than of zinc. Initially, ZDDP was proposed as an antioxidant additive for engine oil, but later on it appeared that it may protect parts of the engine from seizure. There is some humor in the situation, as the ZDDP is actually a corrosion agent. At local temperature increase, when one metal substance is rubbing along another, the ZDP additives react with steel and produce zinc and iron phosphate and sulfides. Reaction products form a relatively soft, porous and patchy film that separates surfaces and keeps them apart. Cylinder bores in an internal combustion engine normally are honed by abrasive stones to produce 45-degree crosshatch of special grooves that retain engine oil during lengthy periods of engine shutdowns. A U-cylinder has areas with a smooth polished appearance with less or no crosshatch visible. As petroleum oil is comprised of non-polar molecules, it flows down from such smooth surface and does not protect the cylinder inside from direct contact with the piston ring during the cold startup of the engine. At this time, the most of the wear goes on. The porous film of zinc and iron phosphates retains some oil and therefore reduces wear at the cold startup of the engine. Therefore, ZDDP is an essential and important ingredient for petroleum-based engine oils. And as the film is relatively soft, the moving parts plow and remove the film, while ZDDP additives in the engine oil react with bare steel surface and rebuild the protective film again and again until the ZDDP additives will be fully depleted. So, the ZDDP additives really protect engine parts from seizure and adhesive wear, but at the high cost of corrosion wear. The American Petroleum Institute is using classification of engine oils according to a level of wear protection. For gasoline engines, the SN class is supposed to provide the best protection from wear, while SM, SL and lower classes are less effective in it. Before pouring oil into the engine, it would be smart to test its performances and ability to protect the engine from wear. Also, it is necessary to monitor performances of the engine oil by taking samples and testing them for wear protection during the use. A wear test machine would be necessary for the test. and such a simple wear test machine as this slide will cost less than $20 but can save considerable amounts of money. In the tests, we measured size of the worn spots. The smaller the spot, the better protection provides the tested oil. The results of wear tests are presented in this slide, and we can see that SN engine oil surpasses SM, SL, and SF engine oils in 1 minute and 10-minute wear tests durations under moderate load 70 Newton. Paraffin oil that has no additives inside does not protect from wear at all. Here, for comparison, worn spots are presented for the best synthetic engine oils under moderate load 70 Newton. We may see that the width of the worn spots in the left picture for SN oil is smaller than the worn spot for the SM oil in the right picture, so as it is supposed to be. All commercial engine oils fail to protect at larger loads and promptly run into seizure. Here we see these ugly images of the surface damage during lubrication by SN and SM oil under heavy load 240 Newton load. Low-class engine oils do not protect from seizure already at moderate loads, and it takes longer for SL oil than for SF oil to run into seizure. With lubrication by neat paraffin oil, seizure happens almost instantly both at moderate and heavy loads. Let us consider some alternative to petroleum oil. Vegetable oils and animal fats were in use as lubricants for 5,000 years or longer. Only in the end of the 19th century, when cheap petroleum oil appeared as a byproduct of crude oil distillation, the bio-oils were not able to compete commercially and have been left by the side wave as lubricants. Meanwhile, due to the great progress in agriculture and biology, some vegetable oils nowadays are cheaper than engine oils and demonstrate decent stability to oxidation to be used as a base fluid for engine oil. Also, vegetable oils provide better lubricity at cold startup, better wear protection, higher load carrying capacity, low volatility, higher flash point, higher viscosity index. And they are not harmful to environment in difference to petroleum oils. Chemical composition of coconut, castor, olein-rich sunflower oils and palm olein are relatively stable to oxidation in comparison with other vegetable oils due to lower content of polyunsaturated fatty acids. Palm olein is a fraction of palm oil that is liquid at room temperature, but it starts to solidify at temperatures below 20 degrees centigrade. Refined palm olein is available in local grocery stores for retail price as low as 80 American cents per liter. All tested bio-oils surpass even the best synthetic engine oils in protection from seizure at heavy loads, 240 Newton. Width of the worn spots is presented for comparison, and we see that the smallest worn spot is for coconut oil and the largest is for castor oil. We may see that neat palm olein surpasses fully formulated engine oils in wear protection under light and heavy loads, while providing similar wear protection under moderate loads. At this slide, worn spots under light load and 1 hour duration are presented for lubrication by palm olein and synthetic SM oil. We may see that neat palm olein protects from wear at light loads much better than synthetic engine oil. At this slide, worn spots under moderate load and 10 minutes duration are presented for lubrication by palm olein and synthetic SM oil. Worn spots are 1.06 mm wide with neat palm olein and 1.16 mm wide with synthetic engine SM oil. We may see that palm olein protects from wear at moderate load better than synthetic engine oil. At heavy loads 240 Newton, palm olein protects from wear slightly better than canola oil. Neat palm olein provides better or about similar wear protection in comparison with fully formulated engine oils. From our experience, as well as from reports of tests done elsewhere, we may conclude that neat palm olein with intrinsic vitamin E as an antioxidant can be used as engine oil, and the recommended oil drain change intervals would be close to recommended ones for petroleum engine oils. Monitoring of viscosity and wear protection of the engine oil are yet necessary. As we mentioned above, performances of lubricants are enhanced with special additives. Actually, petroleum and synthetic oils without special additives do not protect an engine from wear. We developed novel additive packages that are adapted for vegetable oils, but with some modification in their formulation. They can be used also with petroleum oils, also with low efficiency. Below we present results of wear tests of petroleum and vegetable oils with our additives. With additives OK68A, width of the worn spot with paraffin oil is considerably smaller than with the best synthetic engine SN oil. And it is interesting to see that wear protection is not so good if our additives are blended with engine oils of SF and SL classes that are in difference to the paraffin oil have already some additives inside. It seems so that our additives are not compatible with the standard additives in the engine oil, as for the SL oil, wear protection is even worse than with the blend of our additives and the low-class SF petroleum oil. Meanwhile, palm olein with our additives demonstrate very good protection from wear and much better than with paraffin oil. See the right column. Some formulations of our additives are compatible with petroleum oils. Here, worn spots are presented for a blend of paraffin oil with additive pack OK78A. At moderate load, it is 0.89 mm wide, and in the test under heavy load, the worn spot is 1.13 mm wide. So, a blend of paraffinic oil with our additives surpasses the best synthetic SN oil. Polish and wear and formation of a glossy finish on the rotor surface in tests with paraffin oil and our additives under moderate and heavy loads is visible in both pictures, but surface is more glossy for moderate load, that is in the left picture. We tried to find out optimal concentration of the additives. Despite smallest worn spot is measured for concentration of the additives about 10%, we believe that 5% concentration would be optimal. There are two reasons for this. First, our additives are soluble in palm olein, but at lower temperatures that are close to the solidification point of the palm olein itself, the additives may separate and produce emulsion. We find it so that 5% concentration of the additives is more stable than 10%. Also, we may see that from the picture that wear protection is much increasing between 2.5 and 5% blends, while difference between 5% and 10% is not so large. We tried various composition of the additives to find out the best ones. All our additive specs comprise antioxidants, but with different amounts of anti-wear additives and friction modifiers. We believe that good protection at heavy loads is of primary importance, and therefore for palm olein as a base fluid, the additive packs that are close in composition to the OK71B are preferable. However, different compositions of lubricants may be more suitable for gear oil and other applications. So in comparison with synthetic engine oils, our formulations provide much better protection at all ranges of loads, with especially for light and heavy loads. For this slide, tests were made with the seconds of 70 Newton load for 10 minutes and then 240 Newton load for 2 minutes. While Polish and wear was involved in tests with both of the additive packs, we may see the deposition of a layer of varnish lacquer around the worn spot in the right picture. The deposition comprises metal debris and it is healing surface caverns. The layer is hard enough to stay against scratching by fingernail, but can be removed by metal instruments. We believe that the sleek layer of varnish lacquer may protect from wear at cold startup of an engine when the cylinder liner is not yet lubricated. Polishing wear and formation of glossy finish on the rotor surface is visible in both pictures, but surface is better and more glossy for the additive OK68A in the right picture. From pictures presented in this slide, we may see difference in wear with lubrication by our bio-lubricants and synthetic essence oil. While bio-oils produce a glossy surface finish as a result of polishing wear with palm olein and additives, the worn tone of essence oil manifests microscopically irregular surface relief. The smooth polished surface is not capable to retain a lubricating film of petroleum oil, but it is not so with vegetable oils. We decidedly decline addition of ZDDP, either any other corrosion agent, to the bio-lubricants. It results in wear polishing of the cylinder bore that often referred as scuffing. Let us consider lubrication and wear in joints of our bones. Synovial joints are efficient bearings with very low friction that is far superior in wear protection to any artificial bearing and lubricant. Our goal is to learn from the Mother Nature and to reduce radically wear rate and friction coefficients. Synovial fluid, that is a natural lubricant, comprises long polar molecules of phospholipids that can be considered as surfactants in water. Under load, the surfactants in the synovial fluid form bilayer lamellar structures on a smooth surface of cartilage. Repulsion of the bilayer structures due to osmotic pressure keeps adjacent cartilage surfaces separated, while the synovial fluid may slip along the cartilage. We tried to mimic nature and use this insight in the development of our bio-lubricants to reduce friction losses and wear in internal combustion engines. We believe that vegetable oils should be used as a base fluid for lubricants instead of petroleum oils. Vegetable oils are esters of fatty acids, and they are better solvents for various surfactants than non-polar petroleum oils. They also are hydrophobic fluids and protect steel surfaces from corrosion. Not only phospholipids, but also other surfactants can be used. At elevated temperatures, molecules of surfactants are randomly suspended in a solvent, but below some critical temperature, they spontaneously form bilayer lamellar structures on surfaces and micelles in the solvent. Under shear stress, the bilayers slide along each other almost with no friction. So, the base fluid, that is vegetable oil, can actually slip along smooth surface with bilayers of surfactants under shear stress. And also, two adjacent surfaces of lamellar-like structures on them may glide along each other, while osmotic repulsion keeps them apart and prevents direct contact. Therefore, friction coefficient is lower if rubbing metal parts are lubricated by vegetable oils with surfactants than by petroleum oils of the same viscosity. As the polishing wear is progressing, the ability to stay higher and higher loads without any direct contact between the interacting surfaces in their relative motion is increasing. As wear rate with vegetable oils and our additives manifests a tendency to drop in time, then we tested our bio oils under moderate and heavy loads for 100 minutes. Palm olein with additive pack OK71B demonstrate excellent wear protection. In the 100 minutes test under 70 Newton load, the worn volume is about 30 times smaller than with synthetic oil. In this slide, wear rate is presented versus effective pressure, that is the ratio of the load to surface area of the worn spot. It takes about an hour to modify surfaces and radically reduce wear rate if palm olein with OK71B additive have been used. And we can see that established wear rate is about 50 times slower and effective pressure that is 10 times larger than corresponding values for lubrication by synthetic engine SM oil. Meanwhile, in lubrication by neat palm oil, there is only moderate reduction in wear rate during the test. In lubrication by palm olein with OK71B pack, the worn spot has glossy surface appearance in difference to the worn spot lubricated by synthetic SM oil. Obviously, we see a result of wear polishing. This polishing and osmotic repulsion between planar lamella-like structures may keep surfaces apart and reduce wear rate. Palm olein with additive pack OK71B demonstrate excellent wear protection. In the 100-minute test under 70 Newton load, the worn volume is about 30 times smaller and established wear rate is about 50 times slower under effective pressure that is 10 times larger than that values for lubrication by synthetic engine oil SM. We see that it takes about an hour to modify surfaces and radically reduce wear rate if palm olein with OK71B additive have been used. Meanwhile, in lubrication by neat palm oil, there is only moderate reduction in wear rate for the test duration. Commercial engine oils do not protect from wear at heavy loads. Therefore, we can compare only lubrication with neat palm olein and with palm olein enhanced with our additives. We can see from this picture that in 100 minutes test duration, worn volume for neat palm olein is about 2 times larger. For calculated wear rate versus effective pressure at heavy load, we can see that similar to the test under 70 Newton load, it takes about 1 hour to reduce wear rate to about 10 times slower for the olein with our additives, while for the neat palm olein, wear rate drops only 2 times during the wear test duration of 100 minutes. Final wear rate is almost 10 times higher for neat palm olein than for palm olein with our additives. Effective pressure, that is, load capacity for olein with additives, is about twice larger than for the neat palm olein, and final wear rate about 10 times lower for the olein with additives than for the neat olein. Certainly, it is an indication that metal surface gets modified with our additives. Under heavy load, the worn spot for olein with additives appears not only smaller in size but also more glossy in comparison with the worn spot for neat olein. Deep scratching of the surface in the left picture we may explain by presence of abrasive particles in the oil. We may conclude that commercial petroleum-based lubricants protect engine parts from scuffing and seizure at high cost of intensive corrosive wear and at high friction losses in boundary conditions of lubrication and during cold startup of an engine. Wear rate with our bio-oils can be reduced 25-50 times in comparison with synthetic engine oils, while fuel economy may be enhanced up to 30%. Bio-oils can also be used for lubrication of gears, chains, and various bearings to reduce friction losses in wear. Waste engine bio-oils can be utilized for total loss of lubrication. If widely implemented, our bio-oils can radically reduce environment pollution. Our additives with palm olein provide one-time treatment of an engine, as after the conditioning stage to smoothen surfaces in an engine, the amount of additives in the bio-oil can be reduced up to the point that neat palm olein is used with inherent antioxidant and free fatty acids as surfactants, without considerable drop in wear protection and fuel economy. But if instead of palm olein any engine oil from a motor shop with additives of ZDDP is used, the process of wear and corrosion of an engine will be re-established. Can we learn from Mother Nature to facilitate our progress from past to better future? Yes, we can.